In dimensional analysis part 1, we learned the technique. In dimensional analysis part 2, we kind of honed our skills. And now what we want to do is we want to look at some advanced problems in dimensional analysis to really make sure that we have this technique firmly in our grasp. Okay, so here's what we've got. In this first problem, we have this. It says, what is the mass? What is the mass of 6.48 times 10 to the 26 molecules of methane gas? Now, this is the first time in this series of dimensional analysis that we've looked at not atoms, but molecules. This is methane gas, CH4. So we're going to need to develop a way of determining the molar mass of CH4. But we're going to continue with the same technique that we've been using all along. We circle what we know, 6.48 times 10 to the 26 molecules of methane gas. What are we looking for? We want to know the mass of those molecules. So here's what we're going to do. We're going to write down what we know, 6.48 times 10 to the 26th molecules of CH4, place it over 1, times, now we're looking for mass, but we certainly can't go from the mass of, from the number of molecules to the mass directly. We have to go through the intermediate mole. So what we're going to do is, whatever unit is here in the upper left-hand corner, molecules of CH4, is going to go right there. Molecules of CH4, molecules of CH4, moles of CH4. How many molecules of CH4 are there in a mole? Well, how many of anything are there in a mole? 6.02 times 10 to the 23rd. There are 6.02 times 10 to the 23rd elephants in a mole of elephants. There are 6.02 times 10 to the 23rd tennis rackets in the mole of tennis rackets. So what the unit is really is irrelevant. 6.02 times 10 to the 23rd is the number of things in one mole, so that's what we put. This unit and this unit will cancel, and I'm left with moles of CH4 molecules. Now remember, I'm looking for mass, so I need another step. Times whatever unit is there is going to go right there. Molecules is on the upper left-hand corner of this area, then we'll put molecules right there. So we have 1 mole of CH4 molecules weighs how much? How do we determine how much 1 mole of CH4 weighs? We're going to use the periodic table, but there's no methane on the periodic table because methane is a compound. It's not an element. So what we're going to have to do is we're going to have to add up the constituent atoms. Carbon is 12.01. Each hydrogen is 1.01, and there's 4 of them. When I add those two numbers, 12.01 plus 4 times 1.01, I get this number, 16.05. In other words, 1 mole of methane weighs or has a mass of 16.05 grams. Mole of methane cancels with mole of methane, and I'm left with grams of methane. That's what I want. So it's time for me to get my calculator now. 6.48 times 10 to the 26 divided by 6.02 times 10 to the 23rd, enter, times 16.05, and here's the number I get. 1.72761 times 10 to the 4th. 3 significant digits here, 3 here, 4 there. I can only take the lesser of 3 or 4. I'll take 3 significant digits. Underline 1.72. The 7 is bigger than 5, so that will push this 2 up. I get 1.73 times 10 to the 4th. What was the unit? Grams of methane. The mass of this many molecules, 6.48 times 10 to the 26 molecules, is 1.74 times 10 to the 4th grams. Okay? All right. Problem number 1 behind us. Let's look at the next one. This one says, what is the volume? We're looking at volume now. What is the volume of 8.42 moles of ammonia at something called STP? What is STP? Well, it's something called standard temperature and pressure. Standard temperature and pressure is 0 degrees Celsius. Now you may say, well, wait a minute, the temperature at which water freezes. You're right. But that's standard temperature, and standard pressure is 1 atmosphere. And what we know is that at standard temperature and pressure, this is extremely important, all gases have the same volume. 1 mole of any gas at STP or under STP conditions has a volume of 22.4 liters. That's going to be very important in this problem. What is the volume? We're looking for volume of this number of moles, 8.42 moles. We're looking for volume. Put what you know over 1 times whatever unit you have here goes there. Not the number, just the unit. Moles of NH3, moles of NH3. NH3 is a gas at STP. Therefore, it has a volume of 22.4 liters. 1 mole has a volume of 22.4 liters by definition at STP. So moles will cancel with moles. I'm looking for volume. Liters is a unit of volume, and so it's time for me to get my calculator. 8.42 times 22.4. I get this number, 8.8608 times 10 squared. 3 significant digits here, 3 significant digits here. 1 and 1 don't count. I'll take the first 3 numbers. I get 1.88608 times 10 squared. But this 6 is 5 or bigger. It kicks this 8 up. I get 1.89 times 10 squared liters of ammonia. That's my volume. Okay? All right, that's number 7. Let's take a look at the next problem. The next problem says this. It says the density of carbon tetrachloride. The density of carbon tetrachloride is 1.46 grams per milliliter. Okay? 1.46 grams per milliliter. It says a 13.2 gram sample of CCl4 is obtained in the laboratory experiment. What is the volume of this sample in liters? Okay. Now I want you to notice that in this problem, for the first time, in the problem itself, we have more than 1 number. So we have to distinguish between which of these is the number we start with and which is just a conversion. Well, as it turns out, 1.46 grams is the mass of 1 milliliter. That's the conversion that we'll need. This is the number we're starting with, the 13.2 grams. We're looking for volume. So what we're going to do is we're going to break this problem down. We're going to write down what we know, 13.2 grams of CCl4 over 1, times whatever unit is there, goes there. Whatever unit is here, goes here, and whatever unit I want, goes there. Now the first thing I'm going to need to do is I'm going to need to use my conversion factor. I've got 1.46 grams per milliliter. So what I'm going to do is I'm going to say 1.46 grams has a volume of 1 milliliter. Now this will cancel with this, and I'm going to determine the number of milliliters of CCl4 that I've got. 13.2 divided by 1.46, I get this number, 9.04 milliliters of CCl4. Okay? But I want it in liters. So what I'm going to do is this. I'm going to say 9.04 milliliters of carbon tetrachloride, CCl4, times 1, times 1 liter per 1,000 milliliters. There's 1,000 milliliters in 1 liter. Whatever unit goes here, goes there. 1,000 milliliters in 1 liter. That cancels with that. And what I'm going to be left with then is I'm going to be left with liters of CCl4. I don't need a calculator. 9.04 divided by 1,000, remember 1,000 is 10 to the third, but I'm dividing. So 9.404 times 10 to the negative 3, because it's on the bottom, negative 3 liters is my final answer for this problem. Okay? So that's the volume, 9.04 times 10 to the minus 3 liters is the volume of this initial number of grams of CCl4. Okay? All right, that's number 8. All right, number 9. Now this is the final problem. It's a little bit more advanced, but you can absolutely do this if we just concentrate together. So let's go ahead. Here's what it says. It says, how many hydrogen atoms are there in 1.06 grams of ammonia molecules? Now let's picture what we've got here. We've got nitrogen. Ammonia is NH3. We've got nitrogen in the center of the atom, and we've got 3 hydrogen atoms surrounding it. We want to know how many hydrogen atoms there are in this number of grams of ammonia molecules. Okay, so remember, ammonia is NH3, a central nitrogen atom, 3 peripheral hydrogen atoms. Let's start with what we know. 1.06 grams of ammonia. I'm looking for how many, not ammonia molecules, but how many hydrogen atoms. It's going to be a little bit more involved, so stay with me. Write what you know. 1.06 grams of NH3 divided by 1 times whatever unit's here is going to go there. Grams of NH3, I'm going to convert that to moles of NH3. How do I do that? Nitrogen is 14.01 grams per mole. You can look that up on your periodic table. Hydrogen is 1.01, but there are 3 of them. Add those up. 17.04 is the total. That's how you get the molar mass for NH3. 1 mole of NH3 has a mass of 17.04 grams. Now what we're going to do is we're going to cancel this unit with this unit, and that's going to tell us the number of moles of ammonia. We've got 6.22 times 10 to the minus 2 moles of NH3. That's what happens when I divide 1.06 by 17.04. 6.22 times 10 to the minus 2 moles of NH3. But I'm not done yet, because that's not what I'm looking for. I'm looking for how many hydrogen atoms. So here comes the tricky part. Now that I know the number of moles of NH3, I'll reset that number over 1. 6.22 times 10 to the minus 2 moles of NH3 over 1 times, now watch what I'm going to do here. Whatever unit is here goes there. Whatever unit I have here, this is the unit that I want. I want moles of hydrogen atoms. Now watch this. There are 3 hydrogen atoms in a molecule of ammonia. That means if I have 1 mole of ammonia, I'd have 3 moles of hydrogen atoms. Okay? If I have 1 mole of ammonia, I'd have 3 moles of hydrogen atoms, since ammonia is NH3. So now I have the conversion that I was looking for. Moles of ammonia go away, and I'm left with moles of hydrogen atoms. When I do that calculation, here's what I get. I get 1.87 times 10 to the negative 1 moles of hydrogen atoms, and now I'm almost done. Now what I need to know is how many atoms that actually represents. So what I'm going to do now is I'm going to take the 1.87 times 10 to the negative 1 moles of hydrogen atoms and reset that over 1. Reset it over 1 times whatever unit's on the upper left goes on the lower right. Whatever unit I want goes on the top. There are 6.02 times 10 to the 23rd hydrogen atoms per mole of hydrogen atoms. Now moles of hydrogen and moles of hydrogen will cancel, and I'm left with hydrogen atoms. I take this number, multiply by this number, and I get 1.12574 times 10 to the 23rd hydrogen atoms. 3 significant digits here, 3 significant digits here. I can only take 3. 1.1, the next number is 5 or bigger. It happens to be 5. It pushes that 2 up to a 3. My final answer is 1.13 times 10 to the 23rd hydrogen atoms. You are now as of this problem, skilled in dimensional analysis and ready to go on to the stoichiometry series. Thank you, and I'll see you on the next video podcast. Bye-bye.